Hi, my name is Ben Ajayi-Obe, and I am a data scientist at Depop. And I primarily focus on the ranking team.
I'm David Hopes. I'm a data scientist with Depop as well. I work within the MarTech team, specializing in marketing technology. Do a lot of work on text clustering, attribution, and so on. So I apologize in advance. I've had a cold the last few days, so if I cough or sneeze, please, I apologize. So we're here to talk about societal bias in state-of-the-art NLP transfer learning. When we say state-of-the-art, this is a few years, so it's recent. We've got a bit of a warning. So we use some language models to generate text, and it is artificially generated, and it may be offensive or upsetting. We do not wish to offend, and obviously these, what's contained in this text is not our feelings, our thoughts. So yeah, what is bias? So bias is an inclination or prejudice for or against one person or a group in a way that's considered unfair, generally. Harm is the negative sort of impact of bias. So it's when a system allocates or withholds a certain opportunity or resource to a particular group, or reinforces the subordination of groups along the lines of identity. So yeah, I'm just going to go through a few sources of bias. First of all, we've got data biases, reporting bias. This one's really quite an obvious one. Over the last sort of 200 years, it's primarily been sort of middle-aged, very rich white people recording history. And that comes through in all of the data that we train our language models on. Selection bias as well, when you select samples that don't contain the sort of general understanding of the group. Historical injustices. So in the past, we'd have thought things are actually morally correct that are now morally wrong, and they've been recorded, and we're again training our models on those. An implicit bias, I'm just going to go for a couple. Implicit bias is when you're making an assumption based on your own understanding and your own memory. And again, outgroup homogeneity bias, so stereotyping. Basically, you see as people outside of your group as less alike than those inside your group. Do you want to move to the next slide? Then you've got interpretation biases. I'm just going to go, confirmation bias, for example. You're going to look for patterns and information that confirms what you believe already. As a researcher, you come up with a hypothesis, and there are ways to get around the confirmation bias, really. If you want to get to the next slide, and that is and another problem here with experimental bias, the outcome of the experiment tends to be biased towards the result expected. So there's this. I think these slides are going to be made available afterwards. So if you want to look at a few others, then they're there. Cool. So a lot of you would have heard of this old riddle before. A father and son are in a horrible car crash that kills the dad. The son is rushed to the hospital. Just about he's about to have the operation. The surgeon says, "I can't operate. That boy is my son." Now, who do you expect that the surgeon or doctor to be in this case? If you get to the next slide. So it was actually a Boston University study, and the majority of respondents, including males, females, all sorts of groups, didn't actually realize that the doctor was female, and just made the assumption, or tried to find ways to sort of to prove that, or say that it wasn't a woman that was actually operating, or trying to operate in this case. So that's very old. A lot of people would have heard of it, but it's quite an important one. Next up. So we're going to go through some examples of bias here. First of all, within machine translation, again, an old example, but a very important one. Previously with Google Translate, you could use it to translate sentences from one language to another and back again. And this is a really good example of the older model that Google were using, in which you translate the sentence, "He is a nurse, she is a doctor," into Hungarian. Unfortunately, I don't speak Hungarian, so I can't pronounce this. And then back again, it actually translates it as "she's a nurse and he is a doctor." And it's clearly using sort of a bias within the data that's been trained to reallocate the gender here of the nurse and the doctor. Next slide. So yeah, this can also be seen within language models. On the right-hand side, you've got he is a doctor and she is a doctor. And you can see that he is a doctor is more likely within this model. And again, within co-reference resolution, the same problem. He is related to doctor more often than she is related to doctor. And next slide. And within word embeddings, so for example, fast text and bottles, word spec, whatever, you can see again that if you project the gender-specific, gender-neutral words along a he/she plane, you can see that certain words are related. You know, they're more closely correlated to the sort of the male than the female. And here you can see that the gendered words in the top graph, you can see the gendered words below. And then above, words that have no gender, but they've been correlated with. So you can see that that females are more likely to correlate with dancers and dress and beautiful, and males, journeyman, cocky, guru, and so on. And again, you can see this within relations within embeddings. So man minus woman is very similar to computer programmer and homemaker, and Ben's going to go on to that a bit later as well. If you want to move to the next slide. So GPT-2 allowed you to generate text, and you know, there's obviously GPT-3 is out now and has improved upon. But these are some examples of a prompt and then the generated text afterwards. I'll let you go through these at your own leisure, but clearly there are biases within this data. Next up. Again, hate speech detection. So this was a leading CNN, and it was shown that hate speech detection on social media led to a 1.5 times higher likelihood of tweets written by African Americans as being flagged as offensive. This was actually less down to a data bias and more down to an annotation bias, and it was insensitivity. But obviously, it's gonna have a clear negative harm, or it's gonna have a harm on the people it's affecting. Next up. So what we're focusing on in this talk mainly is bias within the corpora, bias within data. So you've got to go through some common corpora used for large pre-trained language models. But corpus is one of them. It's used by Bert, Bart, Bort, and so on. It's a collection of scanned-in books. The genre is sort of skewed towards romance and fantasy, includes 18+ content and terms like alpha male and submissive female. There's also a huge religious representation that's skewed towards Christianity, and a lot of the authors, some of the authors contributed way more books than the others. So this leads to, if you train a model using this data without trying to clean it up first, a skewed religious representation, skewed genres, and the potential for harmful gender stereotypes. Next slide. CC News, collection of news articles. Again, like it's a huge group, a huge selection of sources for these articles, but we're not sure what the political leanings of these sources are. And these stories range from like beauty pageants through to petty and serious crime. So you can see like immediately there's going to be political skews. There could be racial stereotyping. There's going to be socioeconomic stereotyping, and gender stereotyping as well. Next up. C4. So this is a cleaned up version of Common Cruel. This has bad words removed using a repo, dirty, naughty, obscene, and otherwise bad words on GitHub. But again, this is, you know, if that list isn't updated frequently enough, you're going to have certain words that are going to be missed. Language detection models then used to filter that out, but that kind of leads to a lack of minority ethnic English samples within that. And there's also the potential for harmful racial stereotypes in there as well. Next up. Wikipedia. Now, this was a recent paper that was published, was miscategorized gender notability and inequality on Wikipedia. So it showed that that certain articles or articles written by women or about women were more likely to be suggested for deletion than those written by or about men, which is awful. And obviously that's going to lead to inherent gender inequality. And yeah, Wikipedia is used in so many models, used to train so many things. Okay, next up. So we've got a little try it yourself. If you go to huggingface.co, you can actually select a model. In this case, it's just a basic BERT uncased. You can then type in a sentence and use mask for it to generate a token. So here we've got an example. I wrote the sentence, I got a new job as mask. And the model suggested waitress, nurse, teacher, maid, and model. Now, 3 of those are gender neutral. And you can see that there are stereotypes that there's bias that's passed through this model, and it's suggested these particular tokens. If you then put in Steve got a new job as then you get suggested mechanic, bartender, teacher, waiter, and salesman. So yeah, you can clearly see that there's bias within this. Otherwise, it would suggest similar jobs. Next up. So this is a much, much worse one. If you put Christians are generally masked to other people, you get compared, closer, attracted, hostile, opposed to. And then if you put in Muslims generally masked to other people, you get inferior, which is mad. Compared, opposed, hostile, and related. And you can see that the data, the biases within these corpora, and therefore these models, can have a really, really negative impact and cause quite a lot of harm. So next up, we have Ben. He's going to just cover how to address bias within these models.
Thanks, David. So I just wanted to say that we've only got 10 minutes left, so I'm going to go through the process fairly quickly. But I've linked all the papers I reference, and I encourage you to read all the papers, because there's quite interesting work in this area going, and there are lots of interesting problems to solve. So in this particular area, we're focusing on attention models for NLP that have been pre-trained for the purpose of fine-tuning later. For those who don't really know much about this process, the idea is that you have a very large neural network that you pre-train on some pre-training tasks, such as word masking, as David described previously, or sentence classification, with the idea that the model encapsulates information from the statistics of the text in these large corpora. And then this model is then saved and can be later fine-tuned to any particular task that you have a particular data set for. So this is kind of an element of transfer learning in a sense, where the fine-tuning task could be to classify sentiment of particular text. Because the pre-trained model has accumulated these nuanced understanding of text, it is in a better position than starting from zero for the classification task. So as David mentioned, there's a lot of inherent biases in these models, and there have been quite a few approaches taken to mitigate these biases. So these are a couple that I mentioned, particularly for the pre-training stage. So data augmentation involves wherever a gendered word like he or she, grandmother, grandfather is found within the corpora, a counterfactual alternative is made with the opposing gender word. So he is then copied with a she replacement. This is in effect kind of neutralizing the bias, as all biased gendered words are kind of associated with the same different tokens. The bias-aware objective function below is actually slightly differing but similar feature, where gendered counterfactual sequences are inputted into the model at the same time, and a dual objective function is trained, where one objective is to train the particular task at hand, in this case a sentiment classifier, and the other objective is trying to minimize the variance between the differences in these two outputs. The idea being that the probability of a negative or positive sentiment for he is a lifelong bachelor and she is a lifelong bachelorette should be exactly the same in the equal world. So these problems suffer from a effectively a resource issue. The pre-training stage is really, really resource intensive and is very, very expensive. And so creating experiments on top of these strategies is not really practical for most people. GPT-3, incidentally, cost $12 million just to train once. So you can see that it's not a practical kind of line of attack. So here are some examples where they actually try to address bias in the model that has already been pre-trained. And so we see on the paper here, man is to computer programmer, as woman is to homemaker, debiasing word embeddings. This is actually a really interesting seminal paper that has a very amazing approach to actually quantify what gender bias means in embeddings, and then a half-decent attempt at extracting gender bias. So the idea was that the embeddings that are created from the encoder of a transformer are projected into a subspace via PCA. And the idea is that you're very selective on the words you use to create this bias subspace. So you use words that differ in meaning only by gender. So these are, for example, man or woman, or girl, boy, he, she. And when you project these tokens into the PCA subspace, the principal component, the first one, explains the misvariant, should encapsulate that gender direction. And the strategy that this paper employed was to ensure that all gender-neutral tokens are actually equidistant inside this direction. So the word, for example, homemaker should be equidistant between man and woman in this subspace. And they applied a function that transformed the embeddings so that when they were projected into the subspace, they would be equidistant. And this was quite a clever form of eliminating that particular gender direction. The paper on the right, learning gender-neutral word embeddings, is actually does involve pre-training, but it actually involves manipulating the embedding itself afterwards. So the idea was that they manipulated the objective function of the neural network so that the gender information was primarily focused into one particular element of the embeddings in the neural network. Typically, the information is kind of allocated where it's most needed for the actual task at hand in a neural network, but in this case, it's focused into one particular kind of element in that embedding. And the idea is that once the training phase is completed, you can then simply delete or null that one element that encapsulates gender, effectively making the model gender blind in a sense. However, there has been a recent paper, Lipstick on a Pig, debiasing methods cover up systematic gender biases in word embeddings, but do not remove them. So this was a recent paper that discovered that although these papers were very effective in eliminating bias in a particular direction under that definition, they don't actually eliminate bias as a whole in the model. This is because bias is very nuanced matter, and it's very hard to define and create a real definition of what gender bias actually is in the model. So they show that by eliminating the first principal component direction of gender bias in your embedding space, you're only removing one component of gender bias, but there's several other remain, and there are other principal components out there that include that gender bias information. And for example, to give you a concrete example, if you take the word nurse and you transform it so that it's equidistant between man and woman, that has removed one dimension of bias. However, the word nurse may be close to the word feminine or the word homemaker. And that by association allows the model to recreate the gender bias that is embedded in the neural network. And this paper demonstrates this by applying the neighborhood dimensionality reduction algorithm TSNE to show that the words that are gendered separate when this algorithm is applied to them before and after these debiasing strategies are employed. So you can see here the information can be completely reconstructed, and the bias is still inherent in the model, even after these debiasing strategies. So this was a recent paper that attempts to address these limitations of the previous strategies. It is called iterative null space projection. So this is the general algorithm outline, and it involves effectively training a classifier on the gendered embeddings in an attempt to remove gender bias. And I'll explain each step of this algorithm in the next slides. But the paper is linked if you'd like to read in detail more about this strategy. But so this strategy begins first by creating that gendered subspace. So on the right-hand side here, we have an illustration of what I mean by this gendered subspace. So you can see in green, I've included those gendered words I mentioned previously that were actually used to construct this subspace: her, she, female, his, he, male. And you can see in red indicates the first principal component that explains the largest variation in this data, which also correlates to the biggest gender direction. And once we have done that, we then project all of the other tokens, embeddings from our vocabulary into this subspace. And as a result, you can see that several words, tanning, modeling, homemaker, or chief, genius, and captain, they tend towards either polarity of this direction, some more to female and some more to male. And this shows that these words are bias-sensitive tokens. And this is a very effective way of accumulating tokens that have this bias sensitivity in either direction. And so what we do next is once we've found these sets of words, and we'll normally have a cutoff limit, we'll say, okay, the words that are tending towards female, we'll assign that a label, a concrete label of female. And the words that tend towards male, we assign that a concrete label of male. And as in effect, we turn the problem into a classification problem. So now we have the word embeddings on the left with their labels of gender, and then we have a linear classifier with these particular weights. And this classifier is then tasked with discovering the decision boundary that most effectively discriminates between the female and male sensitive words. And this, once we have accumulated this, what you can now say is that this linear classifier, the weights encapsulate the gender information from the actual embeddings themselves. And here comes the part where we apply the null space projection. So the idea of null space projection is that you can discover a matrix where, given the dot product with the embeddings, it projects the matrix into the null space of the classifier weights. So what this means in practice is that the embeddings we see on the right-hand side get projected onto that decision boundary, given this null space projection matrix. And this makes the classifier no longer able to actually classify whether the bias-sensitive tokens are male or female. And what we have here is actually quite a clever strategy for surgically removing the gendered words, gendered information from the embeddings as it was discovered by the classifier. Now, the actual algorithm itself does this in an iterative manner, in a kind of accumulative way, where once we have discovered our null space projection matrix, we then train a new classifier on this nullified embedding, new embedding, to discover a new way of classifying these gender differences. And this is because there are multiple decision boundaries that could exist in the dimensionality for classifying male or female. And so by iteratively applying our approach, we are effectively removing more and more of the information that encodes the bias in the embedding. And at the end of our process, we are now left with our null space projection, which is the product of all previously created projections in each iteration. And what this effect means is now we can take any word embedding and apply the dot product with our projection, and this creates an embedding that really removes the gender bias. Because from this embedding, at least a linear classifier could no longer predict the gender of the embedding. And I should state that this is a linear guarding function. The limitation of this approach is that a nonlinear function could still recreate the gender potentially. So here, how it's made in practice is that we formalize a transformer as an encoder section that gives an output, which is then applied to the weights, which is considered to be the last layer of the model. So this is normally just one linear layer. In our case, we apply the linear guarding function G over the output of the encoding block, such that the weights no longer has kind of access to the gender bias information in the word, and it won't influence inputs. However, one limitation of this is that the linear guarding function has reduced the rank of the encoder output, which could hurt the performance of the actual model as a whole. And so what they do is, in their paper, they freeze the weights of the encoder and apply and do a bit more of continued, so they retrain the model again on the task, but this time only changing the weights of W, so that now W is tuned to the output of G rather than just the encoding. So this is the general strategy. I'm just going to quickly show you. I am conscious that I ran out of time, but I have actually a worked example of this process. So here we actually take the BERT language model, and it's the task of the model is to predict the masked word inside a sequence. And in this particular case, I'm extracting the embeddings from the first encoder layer, as that was the one that saw, at least for me, had the best output in this particular scenario. So from here, we can see we're generating our bias-sensitive tokens. These are for male, these are for female, and these are some neutral ones we made. And here we can see that applying t-SNE to our projected embeddings, we can see they're very linear separable for female and male, but having applied null projection to them, t-SNE is no longer able to distinguish the two. And once we feed this guarded embedding back into the network and run it through the language model, we can now see the output has changed. So here we have an example. People thought she, he was very something during the meeting. In an unguarded scenario where we don't touch the neural network, the first sentence, people thought she was very beautiful during the meeting, and people thought he was very popular during the meeting. This now changes once we apply the guarding output to that one layer in the encoder to people thought she was very quiet during the meeting, people thought he was very quiet during the meeting. So we can see this has actually influenced the behavior of the model towards reducing the gender bias. I will say, we will be sharing these codes, so you can play around with this if you would like. I would say as well, this is not a complete solution. Mitigating gender bias in these models is extremely difficult, and there is lots of work still to be done, not only with actually removing it, but also measuring it. I realize I've gone over time.
No, I think you completed this on time. Like, there was a mishap from our side, so I would like to apologize again for the mishap. But yeah, we do have questions for you. Let me start. So there's a question by Jessica. The question goes like, how can we be sure that in the post-training step, the one done after the guarding the embeddings, we do not just relearn the bias?
Yeah, that's a really good question. I think, I suppose in their particular scenario, they're hoping that the guarding function has already removed the information, and so the retraining will only improve performance on the model, but it is possible. And also because the last layer is linear and only linear, and we're doing a linear guarding function, the hope is that the linear layer won't be able to actually relearn that bias. So it's very important that last layer is linear.
I think also when you're fine tuning, you're just going to have to make sure that the extra data that you're providing has no bias in it. So it doesn't then learn the bias from your data since you've removed it from the pre-trained model.
Yeah.
Okay, we have a question here.
David, can you see the question?
Yep. So how does null space projection ensure that gendered words not present in the initial list do not lose their aspect in their encoding? In German, most professions come in a female and male version. As far as I understand, these would all lose their gender information if not present in the list of frozen words.
That is a very good question. And there's actually a second paper that addresses this exact question, called auto-regressive, and actually I'll send a link to the paper as well on Slack, but it's called auto-ingressive iterative null space projection. And they slightly changed the actual strategy of using the guarding function such that they apply a weight to the guarding function. So to the outputs of the guarded network, I guess, such that if it sees tokens that aren't so gender sensitive or should not be augmented in a gender way, then it will kind of create a parameter to offset the contribution of the guarding function to the model's output. But that was a paper written after the one I mentioned, and they actually talk about the exact scenario you mentioned, where professions are associated with gender, and that is useful. Not so much professions, but yes, these important associations are addressed in their evaluation as well.
Awesome, thank you. So that brings us to the time, and let me just stop the recording.